Hi guys, it's Miss Jackson. We're going to start our stoichiometry today, so I thought maybe I'd pop in and show you my face. It's been a minute since I've seen yours, and I thought maybe you missed me. I miss you guys, something terrible. Go ahead though and get your materials ready so we can get this video going and get it finished. You should have notes, whether you're going to take your own notes or whether you're going to print and write your notes on the document I provided. Get that ready to go, and you're going to need your calculator and your periodic table. So stoichiometry, just to start, is a really big word and it looks a little bit scary, but it really isn't. It's really just about looking at the quantitative relationships between substances and a reaction. What we're going to do today is we're going to marry the ideas of a balanced chemical equation with the mole conversions that we learned how to do. Okay, and stoichiometry is going to link those two together. And you're going to start thinking about your chemical reactions like a recipe. If I start with so much of this reactant, how much of my product can I make? Stoichiometry actually comes from Greek terminology, stoichion for the elements, and then metric means to measure. So it's not really much of a stretch to understand that that means we're going to measure elements. So this is just going to be a series of math problems that we are able to calculate. Maybe if I can get it to play. Yeah, these are chemistry math problems, and they're going to determine how much of a reaction, or how much is produced or used up or is necessary in a chemical reaction. So let's go ahead and get started. For stoichiometry, you're going to have two things. You're going to have a balanced chemical equation, and you're going to have some measured values given to you. So we're going to focus on this week what we're going to call the mole ratio. And this is the same ratio that we looked at when we did balancing chemical equations. These are going to be the coefficient ratio. And they can represent molecules or they can represent moles. That's going to be where we get the mole ratio referenced here is from the balanced equation that you're going to have to write first. When you're looking at these math problems, if you have two or more chemicals, it's going to be a stoichiometry problem. That means we're going to convert from this chemical to another chemical. That's stoichiometry, as opposed to what we did last week, going from grams of this material to liters of the same material. That is not stoichiometry. Conversion factors, but not stoichiometry. All right, so let's look at this mole-mole ratio. So here is what's called the Haber process, and this is how we commercially produce ammonia for sale. We take nitrogen gas, we react it with hydrogen gas, and we produce ammonia. You should remember from balancing that we're trying to make both sides of our chemical equation equal. I can't create atoms, I can't destroy atoms, so I have to have the same number of each kind of atom on both sides. So it takes two nitrogen atoms, one molecule, the understood one. I've got two nitrogen atoms here, and I've got two nitrogen atoms here. I've got three molecules of hydrogen, which is 6 hydrogen atoms, and I've got 2 molecules of ammonia, which gives me 6 hydrogen atoms. The ratio is 1 to 3 to 2. Okay, and no matter what happens for this chemical reaction, the ratio of nitrogen to hydrogen to ammonia is always 1 to 3 to 2. Okay. If I want to look at that in a larger sample size, I'm looking at a mole instead of a molecule. This isn't convenient to use. We don't work with individual molecules. They're way too little. So we look at sample sizes like the mole. So if I have 1 mole of nitrogen, it's going to react with 3 moles of hydrogen, and it will always produce 2 moles of ammonia. And this is why we have to have that balanced chemical equation, because we need that ratio. That ratio is the key to doing the stoichiometry. That ratio of elements is going to be the same regardless of those units, except grams. We can't use grams. We have to have moles here, okay? All right, so let's look at a different equation. So this is the combustion of propane. This is what we have in our gas grills. I need 1 molecule of propane to react with 5 molecules of oxygen. And when I do, I get 3 molecules of carbon dioxide and 4 molecules of water. If I look at it on a larger scale, I look at moles. 1 mole of my propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. What this balanced equation allows us to do is to look at any two of our compounds or elements in our equation and compare those two. In this reaction, for example, for every 1 mole of propane, I need 5 moles of oxygen to react with it. It's just like a recipe. If I have 1 mole of propane, I need 5 moles of oxygen. If I had 2 moles of propane, I would need 10 moles of oxygen. The ratio remains 1 of these for 5 of these. Knowing that my ratio is 1 to 5 to 3 to 4, I can compare any two that I want at any time that I want. For example, if I look at the equation here, my ratio that relates carbon dioxide to oxygen gas is 3 moles of carbon dioxide for every 5 moles of oxygen. I can write it this way, 3 moles of carbon dioxide for 5 moles of oxygen, or I could flip it over and I could have 5 moles of oxygen on top and 3 moles of carbon dioxide on the bottom. Because these are necessary in this ratio for this equation, these two have equivalent values, and so they can be written as a conversion factor. And it's these ratios that will allow us to change from one element into a different element. Okay? It's just like if you make cookies. You may have 10 pounds of flour and 2 eggs. Well, 10 pounds of flour makes one number of cookies, and 2 eggs makes a completely much smaller number of cookies. Okay, and so we have to use that recipe to figure out how much of each reactant we need. So for 2 eggs, I may only need 2 cups of flour. And I'm making that up, I don't remember a cookie recipe. All right, so let's see how this looks in practice. So let's do an example. Okay, now I'm still working on the timings of some of these slides, so you're going to have to go back in. When we work an equation, okay, so here's an example. How many moles of carbon dioxide gas would be produced from 6.25 moles of oxygen gas? So the first step is we have to have a balanced equation, and we're going to use the same equation we were just looking at, the combustion of propane. All right. When I look at my equation, I'm going to do what I always do. I'm going to start with what's given, and my given amount is 6.25 moles of oxygen gas. So that's going to be where I start. Okay. So I start with 6.25 moles. And now I'm going to use my balanced chemical equation for the combustion of propane, this is propane, to figure out how many carbon dioxide moles I'm going to make. Looking at my equation, okay, I'm going to have to figure out which 2 chemicals I'm going to look at. Well, I'm going to look at carbon dioxide and oxygen. Okay, now I have to look at my conversion factor. I know that my ratio of carbon dioxide to oxygen is 3 moles of carbon dioxide to 5 moles of oxygen, but one of them has to go on bottom and one has to go on top. Hopefully you remember that what we cancel goes on bottom and what we want to convert to goes on top. So my conversion factor looks like this. I'm going to have moles of oxygen on the bottom. My 5 moles of oxygen go to the bottom, and I compare that to the 3 moles of carbon dioxide on the top. So now I can look at my equation. I can see that my units are going to cancel. Moles cancel, moles of oxygen cancel, and all I have left are moles of carbon dioxide. So I finished the calculation or the setup for the problem in example 1. Now I complete the math. I take 6.25 times 3 equals, and then divided by 5. You should get 3.75 moles of carbon dioxide as your final answer. Okay, so these are real small calculations this week, really short, small step equations. The next sample problem I'm going to show you also is on your note page. I just don't have the transitions working the same way. Okay, so this is just kind of the whole kit and caboodle at once. The second equation, or the second problem, is still using the combustion reaction for propane, but I've asked a different question. How many moles of propane gas would be needed to react with the same 6.25 moles of oxygen? So in my equation, I know that I am starting with oxygen and I'm looking for moles of propane. So as before, I start with what's given, 6.25 moles of oxygen. And these are the two pieces that I want to look at for my conversion factor. 5 moles of oxygen goes on bottom so that my units will cancel. And the 1 mole of propane goes on top so that is my final answer. I have 1 mole of propane because the number in front of propane in the equation was 1. When I do the math, 6.25 times 1 divided by 5 is 1.25 as my final answer. So this is just the beginning of stoichiometry. There's actually more that we will get to next week, but this week's focus is completing the mole to mole ratio changes. Anytime you have one substance, you've got to be in moles to use your ratio. This is your mole-mole ratio up here, 1 to 5 to 3 to 4. And this is what allows us to convert from one substance, in this case oxygen, to a different substance, in this example, propane. That is all tied to that balanced chemical equation. You've got 5 practice problems on the back of your note paper, and you've got the answers in random order at the bottom. So give those a try and check your work. Don't forget you can reach out with an email if you run into trouble, and you can also join my conference hour any day you like, Tuesday through Friday from 10 to 11. So if you have questions, don't hesitate to reach out. See ya. Bye.